An example that will motivate our use of Laplace transforms to solve differential equations is electric circuits. So we're going to consider a closed circuit with a resistor R, and on a circuit diagram it's usually represented by one of these squiggly lines, and a capacitor with capacitance we'll call C, and a capacitor stores charge. And then an inductor with inductance L. So an inductor is a solenoid coil like that. We'll say it has inductance L. And then we're also going to hook that up to a battery. We'll call that battery V of T, which is supplying voltage. Now, in order to describe this electrical circuit, we're going to use Kir Kobs Law, which says that in a closed circuit, the impressed voltage is equal to the sum of the voltage drops in the circuit. Okay, so according to the laws of electric circuits, the charge is given by Q, and then the current is going to be the derivative of charge, which is dQ dt. Now, the voltage drop across a resistor is equal to I times R, or we can write this as R dQ dt. And then the voltage drop across a capacitor is Q over C, and the voltage drop across an inductor is going to be L di dt. Another way we can write that is L d squared Q dt squared. Okay, so if we combine these laws, this will yield actually a second order differential equation. So what we're going to do is we're going to take the voltage drop across the inductor, L d squared Q dt squared, plus the voltage drop across the resistor, R dQ dt, and then plus the voltage drop across the capacitor, 1 over C Q, and all of that is supposed to equal the impressed voltage, which we said is the battery, which is V of T. Now, we're going to just first look at this second order differential equation. Something I want you to notice is that R, which is the resistance from the resistor, is like the friction term that we had in the mass spring problem. So the resistor does what it says. It offers resistance. It provides friction for this circuit. Okay, but this is a second order differential equation for the charge. Usually we want to talk about the differential equation for the current. So we're going to take the derivative of all three of those terms and recognize that the derivative of charge is current. So this actually gives us L d squared I dt squared plus R di dt plus 1 over C times I. The derivative of Q is I, and that's going to be the derivative of the voltage. And this is generally the second order differential equation that you get, that you would want to look at when you're examining a circuit that has a resistor, a capacitor, and an inductor. And so you see that this second order differential equation should have the same types of behavior that we would get with the mass spring system. So what I'm going to do is I'm going to open up slopes, and I'm going to plot two things in slopes. I'm going to plot the current, and then I'm also going to plot the power, and the power for this circuit is going to be equal to I squared times R. So those are the two things that I'm going to plot. So I'm going to open up slopes, and I'm going to open up the oscillations, and we see our mass spring system here. But if we use our finger and slide this over, we now can look at the electric circuit. Now, this electric circuit has no resistance. So if I push play, the power is 0 because the power is equal to I squared times R. and R in this case the resistance is 0, but this circuit will just kind of oscillate forever if it's missing resistance. But if we add a little bit of resistance, okay, so then what will happen is that the resistor in this circuit, which is represented by the squiggly line, we'll think of that resistor as being like a light bulb. Okay, so the resistor is transferring energy to the light bulb and then it's lighting up. And so then we can see for this underdamped oscillator that it just kind of blinks on and off the light bulb. Okay, now if we increase the resistance, okay, so that it's now an overdamped oscillator, okay, then when we push play, I'll kind of zoom out here so that you can see, when we push play, and I will give it more time to drop off, okay, then what happens is that the light bulb kind of just slowly burns out. And that's an example of the second order equation that describes an RLC circuit.